Okay, so now we're finally going to start talking about asymptotic analysis in a slightly more formal way. Let's motivate that by talking about brute force. So for lots of non-trivial problems, what you do essentially to solve the problem is you look at the entire space of possible solutions and you pick out the right solution based on the size of the input, based on the algorithm. But this typically is an exponential problem because there's lots of possible solutions. So this is unacceptable in practice. So brute force can work. Sometimes it doesn't. What we're interested in is worst case running time. We want to obtain a bound on the largest possible running time of the algorithm on input of a given size n. But we don't want to use brute force. So that leads us to trying to look at polynomial time algorithms. We start with this desirable scaling property, which is when the input size doubles, the algorithm should only slow down by some constant factor c. Or a better way to put that is if we have constants c and d both greater than 0, such that every input of size n, the algorithm's running time is bounded from above by c times n to the d computational steps, so that the upper bound of how complex the algorithm is, it can be described by a polynomial. And so this is what a polynomial algorithm is. So now if we combine worst case and polynomial, we can say that an algorithm is efficient if its running time is polynomial. You have to be careful about that because, for example, if I have 6.02 times 10 to the 23rd times n to the 20th, then that's really actually a polynomial time algorithm, but it's pretty useless in practice because the exponent is so large. The good news is that for most of the algorithms that we are interested in, the polynomial time constants are relatively small. And we'll see that by doing a bunch of examples and looking through things. There are exceptions. There are some polynomial time algorithms that have very large constants or exponents, and those are pretty useless in practice. On the other hand, if you go back to the brute force type of case, there are some exponential time algorithms that are used because the worst case, that exponential time example, is very, very rare. And so there are, despite the fact that it is an exponential time algorithm, it can be very useful. So why does this matter? Why does all of this time and exponents matter? Well, it matters because of how fast computers are. Now, this table's fairly old because it's just talking about a processor that can perform only 1 million high-level instructions per second. That's not the case these days. You're probably closing in on 1 billion high-level instructions per second. But it's clear that what happens, and you can see this, is that if you have a polynomial time algorithm, then the time is much faster than for, say, the 2 to the n column or the n factorial column, where very quickly you get very, very fast and very, very slow algorithms. Okay, so now let's start to define these orders of growth. First one, for upper bounds. If I have a function t of n, I can say that t of n is big O of f of n if there exist two constants, c greater than 0 and n sub 0 greater than or equal to 0, such that for all values of n greater than or equal to n sub 0, we have t sub n is less than or equal to c times f of n. So past some initial threshold value n sub 0, every value of t is smaller than c times f of n. So c times f of n is an upper bound for that. Lower bounds. Again, given a function t of n, we say t of n is big omega of f of n if there exist two constants, c greater than 0 and n sub 0 greater than 0, so that for all n bigger than n sub 0, every value of t is bigger than c times f of n, bigger than or equal to, so that c times f of n is a lower bound for t sub n. It'll never be smaller than that once you get past that threshold value n sub 0. And then finally, we have a tight bound where we say t of n is big theta of f of n if t of n is both big O of f of n and big omega of f of n. So that there's a couple of constants, c and n sub 0, beyond which t of n will end up being between these two functions. So all of the values of t of n will end up in between these two bounds. So for example, if t of n is equal to 32n squared plus 17n plus 32, well, then we can say that t of n is big O of n squared, which seems perfectly fine, but it's also big O of n cubed, because we don't say how tight the big O boundary has to be. T of n is also big omega of n squared, because in this case you can look at the low order terms and t of n is always going to be at least as big as n squared. And it's also big omega of n because it's always going to be bigger than some linear time function. And it's big theta of n squared because it is both big O of n squared and big omega of n squared. T of n is not big O of n because of that high order term. It's always going to be bigger than that. It's not big omega of n cubed because that's too big. And it's not big theta of n or big theta of n cubed because it's either going to be too big or too small. When we say that t of n is equal to big O of f of n, that's a slight abuse of the notation, in part because this is not a transitive function. So if we have two functions, f of n, which is 5n cubed, and g of n, which is 3n squared, then f of n is big O of n cubed, but g of n is also big O of n cubed, but f of n is not equal to g of n. So we're playing a little fast and loose with the notation here. It would be better if we would say that t of n is an element of big O of f of n, but nobody ever says that. Okay, so some examples, some questions. When is t of n big O of f of n? So, as an example, if we claim that if we have a function t of n, which is a sub k times n to the k plus a sub k minus 1 times n to the k minus 1, all the way down, that's clearly a polynomial of order k. And then we say, if that's true, then we say that t of n is big O of n to the k. And the question is, how can we show that? And I'm not going to tell you right now. You're going to have to do it yourself. You can either stop the video to do that, or you can do it later. The hint at the bottom is important. You need to find acceptable values for c and n sub 0. And use them to get to big O of n to the k. Okay. Another question. How good is big O of n to the k? So if we have another example, another claim that we would like to make, for all k greater than or equal to 1, that n to the k is not equal to big O of n to the k minus 1. Now, that may seem obvious, but it would be nice if we could actually prove that so that we could say that a function that is big O of n to the k is not big O of n to the k minus 1. And the hint here is it's not an inductive proof. So we can talk about that one later as well. Or you could stop the video right now and go off and make that proof. Okay. Another one. Why should we use big O of f of n rather than big theta of f of n? You would think you would want to use big theta of f of n because it's the tight bound. And that would be nice. But what we're normally interested in is actually the upper bounds of performance rather than having tight lower or upper bounds. In most cases, we don't really care that much about the lower bound. We're really concerned with how bad performance can get. And so, for example, this is another set of questions for you to answer offline. If I have t of n equal to 1/2 n squared plus 3n, then which of the following 4 statements are true? And I'll let you do those and we'll talk about them later. There's some properties of the big O, big theta, and big omega notations that you can take to the bank. And we could prove these, but we're not going to. So, for example, the first one is if f is big O of g and g is big O of h, then f is big O of h. So transitivity holds, and the same thing holds for big omega and big theta. And additivity holds for all 3 of the measures as well. And so that might be important later on. And then finally, one last proof. For every pair of positive functions f of n and g of n, we're going to claim that the pointwise maximum fg, so that's the set of maximum points taken from the various values of those 2 functions. We're going to claim that set of points is big theta of f of n plus g of n. And so the question is, can you prove that? Again, it's not an inductive proof. This one's a direct proof, though, pretty much. So good luck with that one. And that's really the end of part 1 for asymptotic analysis. Stay tuned for part 2.